Welcome to another IB Environmental Systems and Societies video. Today's topic is 7.2, Climate Change Causes and Impacts. This topic helps us understand not just how our climate is changing, but why these changes are occurring and what they mean for both the environment and human societies. This image behind me shows a global temperature map with warmer colors indicating higher temperatures. This is a visual representation of the warming patterns that we're going to be discussing in this video. So let's get into it. One of the most important concepts to grasp is that while climate change is nothing new in Earth's history, what we're experiencing today is unprecedented. First, let's examine this graph showing Earth's climate rhythm over 400,000 years. Three key measurements are tracked here: CO2 levels in blue, temperature in orange, and sea level in green. Throughout this entire period, CO2 levels naturally fluctuated but never exceeded 280 parts per million, or ppm. However, take a look at that dramatic spike at the right edge of the graph. That's where we are today, well over 420 ppm. This extraordinary increase has occurred in just the last 200 years, and that coincides with the Industrial Revolution and the rise of our use of fossil fuels. To understand climate change, we first have to be clear about the difference between climate and weather. The desert scene in this slide helps illustrate this distinction perfectly. Weather is what's happening in the atmosphere at any given moment, like those storm clouds that you see gathering in the image. Climate, on the other hand, describes the long-term patterns of atmospheric behavior in an area. So while this desert might experience occasional rainy weather, its climate is characterized by hot, dry conditions year after year. This remarkable diagram shows us one of Earth's most important climate-regulating mechanisms, the global ocean conveyor belt. This massive system of currents acts like a planetary heating and cooling system. Warm surface currents, shown in red, transport heat from the equator towards the poles. As this water cools, it becomes denser and it sinks, forming deep, cold currents that are shown in blue. This process helps distribute heat around the planet, and it influences climate patterns around the world. When we disrupt these patterns through global warming, we're essentially tampering with Earth's thermostat. The relationship between CO2 and global temperature reveals one of the most compelling pieces of evidence for human-caused climate change. This graph compares CO2 levels and temperature over an 800,000-year period. That's an extraordinary window into Earth's past. The blue line shows CO2 concentrations, while the red line tracks temperature changes. Notice how these lines dance together throughout history, rising and falling in remarkable synchronization. This pattern tells us something crucial. When CO2 levels change, temperature tends to follow. While some might argue that correlation doesn't equal causation, 800,000 years of consistent correlation strongly suggests a causal relationship. One of the most visible impacts of climate change is the intensification of extreme weather events. Let's use Hurricane Katrina, shown in this satellite image, to understand why. Think of the ocean as Earth's biggest solar energy collector. As greenhouse gases trap more heat in our atmosphere, oceans absorb a lot of that extra energy. Hurricanes draw their strength from warm ocean water. It's like fuel for these big storms. So when we warm the oceans, we're essentially providing more fuel for hurricanes. And that, of course, leads to more powerful storms. It's a direct chain reaction. More greenhouse gases leads to warmer oceans, which leads to stronger hurricanes. Looking towards the future, these graphs show different scenarios for greenhouse gas emissions and their potential impacts. The colors represent different policy choices and actions that we might take. The red pathway, RCP 8.5, shows what might happen if we continue business as usual, potentially leading to temperature increases of 3.2 to 5.4 degrees Celsius. The blue pathway, RCP 2.6, represents aggressive action to reduce emissions. This isn't just about numbers on a graph. It's about the kind of future we choose to create. This pie chart breaks down global greenhouse emissions by sector. The energy sector, shown in red, dominates at 73.2% of total emissions. But let's look deeper. This includes not just electricity generation, but also energy use in buildings, in transportation, and in industry. Here we see how global trends manifest at a local level, using Cambodia as an example. The graph shows temperature changes since 1925, with a clear upward trend starting around 1975. This illustrates a really important point. While climate change is a global phenomenon, Its impacts are felt locally, and they can vary pretty significantly from region to region. This sobering map shows potential sea level rise impacts on North America. The annotations tell us that entire regions, including Florida and much of the Atlantic seaboard, could be submerged. This isn't science fiction. It's a possible future based on our current emissions trajectory. Notice how major coastal cities where millions of people live are particularly vulnerable to the sea level rise. When examining the debate around climate change, it's important to look at what the scientific community actually says. This infographic shows that 97 out of 100 climate experts agree that humans are causing global warming. This isn't just a casual survey. It represents a comprehensive analysis of peer-reviewed scientific literature. The small number of dissenting voices often receives disproportionate media attention, and that can create the illusion of more scientific disagreement than actually exists. This pie chart reveals something fascinating about public attitudes towards climate education. Despite the political controversy surrounding climate change, 77% of Americans, that combines strongly agree and somewhat agree, support teaching children about climate change causes, its consequences, and potential solutions. This suggests a real disconnect between public acceptance of climate science and the sometimes heated political discourse around the topic. This seemingly overwhelming graph actually teaches us something important about climate science. Each colored line represents a different climate model projection, and their variation shows why climate modeling is so complex. But take a look at how they all trend in the same general direction, upwards. This illustrates that while there's uncertainty about precise numbers, there's strong agreement about the overall trend. It's like weather forecasting. We might not know exactly how many inches or centimeters of rain are going to fall next week, but we can be pretty confident about the arrival of a major storm system. The World Bank's Climate Change Knowledge Portal, shown here, represents a crucial tool for understanding climate impacts at local and regional levels. The interface lets you examine both current conditions and future projections for nearly every single country on Earth. Notice how it combines different types of data, temperature, precipitation, and other variables, to create a comprehensive picture of climate change impacts. This diagram illustrates how climate change affects multiple systems at the same time. From changing rain patterns to species migration to ocean acidification, each impact connects to and often amplifies others in a type of feedback system. It's particularly important to note how these changes affect both natural systems and human societies. It is an environmental systems and societies class after all. Agriculture to human health to economic systems. Let's examine these maps that show projected changes in forest types across the eastern US. What we're looking at is a dramatic shift in biome distribution between 1960 to 1990 and what's projected for the years 2070 to 2100. Notice how the maple beech birch forests that are shown in red are projected to nearly disappear from the landscape. This isn't just about losing certain tree species. It represents a fundamental reorganization of entire ecosystems. These changes happen because different tree species have specific temperature and precipitation requirements. As climate conditions shift, areas that once provided ideal conditions for certain forest types may not be able to support them anymore. This has cascading effects on everything from wildlife habitat to ecosystem services like water filtration, erosion control, and carbon storage. These four maps tell a story about future water availability. Starting at the top, we see projected precipitation patterns, but that's only part of the story. The second map shows projected evapotranspiration, essentially how much water plants and soils are going to lose to the atmosphere as the temperatures rise. The third map combines both of these factors to show the overall water balance. And then the fourth shows how dramatically these patterns are going to change between 2005 and 2099. What's particularly concerning here is that many agricultural regions are projected to experience really significant water deficits, and that threatens food security and ecosystem stability. Take a look at these forest distribution changes over time. You can see a stark transformation. The map comparison shows how climate change is effectively pushing ecological zones northward. This isn't just about forests moving. It's about entire communities of organisms having to either adapt, relocate, or die. Some species are going to be able to migrate. Others may face local extinction if they can't keep pace with the rate of climate change. This raises important questions about conservation strategies in topic 3. We try to preserve ecosystems as they are, Or do we help species migrate to new areas that will be more suitable in the future? This WWF diagram beautifully illustrates the complex impacts of even a 1.5 degrees Celsius temperature increase on biodiversity. Notice how different species groups are affected differently. 6% of insects, 4% of vertebrates, and 8% of plants are projected to lose more than half of their climatically determined geographic range. This diagram also shows how Arctic ecosystems are especially vulnerable, with the prospect of ice-free summers becoming more and more frequent. These changes ripple through food webs and ecosystem relationships in ways that we're still trying to understand. This infographic shows the interconnectedness of biodiversity loss and climate change. The arrows between different parts show how one change leads to another in a complex web of cause and effect. That's your feedback mechanisms that we've talked about earlier in the syllabus. Especially noteworthy is how changes in one area, such as reduced primary production, can trigger a lot of downstream effects on ecosystem functions. This shows why protecting biodiversity isn't just about saving individual species. It's about maintaining the stability of entire ecological systems. And that comes back to our conservation strategies that we studied in topic 3. The map we're looking at shows potential coastal flooding impacts, with red dots showing cities of over 10 million people each. This isn't just an environmental issue. It's a massive societal challenge around the world. Consider that these coastal regions aren't just residential areas. They're centers of economic activity, of cultural heritage, and critically important infrastructure. The projected inundation would force unprecedented human migration, and it would require enormous resources for adaptation or relocation. That's a lot of money that most governments don't currently have. This diagram walks us through the process and impacts of ocean acidification, from its drivers all the way through to policy options. As atmospheric CO2 increases, more is absorbed by the oceans, and that leads to increased acidity. This chemical change has profound biological effects, particularly on organisms that build shells or skeletons from calcium carbonate. The flow chart shows how these biological changes cascade through marine ecosystems, ultimately affecting human societies through impacts on fisheries, coastal protection, and food security. When we study climate change feedback mechanisms, we need to understand both positive and negative feedback loops, and equally importantly, their time lags. This picture shows how desertification, biodiversity loss, and climate change are all interconnected. Notice how each process feeds into the others. For example, when climate change increases extreme weather events, this leads to soil erosion, and that reduces carbon storage capacity, which then accelerates climate change further. These cycles can take decades or even centuries to fully manifest, and that makes them especially difficult to address. Let's think about this feedback mechanism diagram as a practical tool. When we examine each arrow and connection, we can identify potential intervention points. For example, the link between the soil erosion and the reduced carbon reserves suggests that soil conservation practices could help mitigate climate change impacts. This systems thinking approach helps us understand not just individual problems, but how they interact and amplify each other over time. This cartoon presents a deceptively simple image of the climate change debate. While it might be tempting to categorize people as either alarmists or deniers, the reality is far more nuanced. The scientific evidence suggests that neither extreme position is helpful. We need balanced, evidence-based approaches that acknowledge both the seriousness of climate change and the complexity of addressing it. This is where our understanding of environmental value systems becomes especially relevant. This slide raises two fundamental questions about climate change for TOK and international mindedness. First, as an international issue, how do we coordinate action across borders when impacts and responsibilities aren't evenly distributed? Second, from a TOK perspective, how reliable are our predictions about future climate impacts when they're based on past data? These questions should challenge you to think not just about the science, but about equity, responsibility, and the nature of knowledge itself. That's it for IB ESS Topic 7.2 Climate Change Causes and Impacts. Until next time, happy learning.